So welcome to the lecture on multi-degree of freedom system. We will discuss today the flexibility influence coefficients. So what is flexibility? As flexibility is reciprocal of the stiffness. And we know that in any vibrating system we have mainly three elements: spring, mass and damper system. So for a spring mass system, that is undamped multi-degree of freedom system, we have already derived the equation of motion that comes into the form of a matrix. So the equation of this motion, that is mx double dot plus k x equal to 0. And here I said that this M is mass matrix, and here this K is stiffness matrix. Now what is the flexibility matrix? So here, because flexibility is inversely proportional, that is the reciprocal of the stiffness, so here the flexibility matrix, let's say A, that is equal to K inverse, and similarly K inverse is equal to A, or A inverse is equal to K. So here we can have we can also write that A into K, that is equal to an identity matrix, or K into A is equal to identity matrix. So here we have, now if in this equation we multiply with, so we have this equation mx double dot plus kx equal to 0. Now we multiply with k inverse, so we will have k inverse m x double dot plus k okay, so here it is k inverse k x equal to 0. Now here k inverse is, we can write the flexibility matrix. So this is A m x double dot plus, here k inverse into k is I, and when we multiply I with x, it is x, so that is 0. So finally our equation of motion results to be in the form of mass matrix and flexibility matrix. So therefore if we can we can prepare the flexibility matrix, we can also write the equation of motion directly using the flexibility matrix. So flexibility matrix A has its coefficients. So here we have like A 1 1, A 1 2, A 1 J, A 1 N. If it is N into N, here A 2 1, A 2 2, A 2 J, A 2 N. Now we have here A, I1, A, I2, A, I, J, A, I, N. Here we have A and 1, A and 2, A and J, A and N. So we have this is N into N matrix for that is flexibility matrix, and the elements of this matrix are known as flexibility influence coefficients. So if we take this Aij, one element Aij, so how we will define this Aij and how we will obtain Aij, because if we know any particular these elements, if we know all these elements, we can prepare a flexibility matrix for that problem. Now Aij means what? So we will define here Aij. So suppose we have some member here, and here are 2 points, that is I and J. So Aij is defined as the value of deflection at I due to a unit load applied at J. So if we have this flexibility influence coefficient Aij is defined as the deflection at I when we apply a unit load J at J, that is unit load, and we measure what is the deflection that is coming here, and that is Aij. Similarly, Aj is the deflection at J due to a unit load applied at I. So here we are applying a unit load at I and measuring deflection at J. So now the reciprocal theorem, Maxwell's reciprocal theorem states that this Aj equal to Aji. So it means that the deflection due to unit load, deflection at I due to unit load at J is equal to the deflection at J due to unit load at I. Now here we have Aij, Aji, and we have also Aii. So Ii means we have the deflection at I and unit load at I, so at the same point. So we are applying the load at the same point, unit load, and measuring the deflection at the same point. So Aii or Ajj. So these are called the direct influence coefficients, and these are called the cross influence coefficients. Now as we have defined what is the flexibility matrix, what are the flexibility influence coefficients. Now if we want to prepare this flexibility matrix, how we will do it? So I take one example, and we can apply some these rules that we have already studied, this new this equilibrium equations, and we will find these coefficients. So now we take one problem, and we try to derive this flexibility coefficients. So here we have 2 degree of freedom system, and comprising the two masses m1 and m2, and two stiffness elements, that is k1 and k2. We assume that the surface on which these masses are resting, that the friction is negligible or zero. So we are not considering the friction. And now we have to find the flexibility matrix. So because we have this 2 degree of freedom system, so our flexibility matrix will be a square matrix having 2 into 2. So we will have A, the flexibility matrix, that is having A1 1 and A1 2 and A2 1 and A2 2. So now we have to find the values of these coefficients, and so we will find the flexibility matrix. So now if we want to find this A1 1, A2 1, so let's now we do like this. So we have so now what we are doing, because the flexibility coefficients are defined as the deflection at, so Aij is defined as deflection at I due to a unit load at j. So it means we have to apply a unit load at one point and measure the deflection at other points. So if I apply here at, so this is 1 and this is 2, so this is first mass. So I apply a unit load here like this, So this is unit load. So this is unit load here. And now I want to measure the deflection. So deflection here and deflection here. So what will be deflection here? That will be A1 1, because I am applying a load, unit load at 1, and I am measuring deflection at 1. So I am applying the load at j. So here I is equal to j is 1. Now what will be the displacement at mass 2? So I am applying load 1. So here I am applying and measuring at 2. So A2 1. So I am applying load at 1 and measuring deflection at 2. Now we have to make the free body diagram to find the equilibrium equations. So here we have this mass, first mass, and this first mass we have load here, unit load. Then because we have some deflection here, we will have a spring force here, that is K1, because this is K1 and this is K2. So K1 into A11, because A11 is the deflection and K1 is the stiffness. So the spring force acting due to the movement is K1 into A11 in the opposite direction. Now there is a spring K2 and this will apply a force. So K2 into, this is moving A21, this is A11. So here A21 minus A11. So the net force that is due to spring is the relative motion, relative displacement between these of this spring. So that is 81 if we assume greater than A11. So 81 minus A11 into K2. Now on the second mass, the we have to make this free body diagram of this mass. So this mass is M2. On this mass we don't have any external load, as in this case we have unit load. So this mass is only subjected to a load due to a force due to the spring K2, and that is the same magnitude but the direction is opposite one. So now we have to balance these equations. So for this equation number 1, we have these two forces in this one direction and this is opposite direction. So we will have K1 A11 minus 1 minus K2 A21 minus A11 equal to 0. So the net total sum of the forces are 0. Similarly for the second mass we will have K2 A21 minus A11, and so only this force, and so that is equal to 0. So from this equation, so this is equation number 1 and this is equation number 2. So from equation 2 we will have, from equation number 2 we will have A21 equal to A11, because here this is zeros and K2 can't be 0 because it is a finite stiffness of this spring 2, and therefore we will have A21 equal to A11. Let's say this is equation number 3. Now from equation number 1 So from equation number 1, K1 A11 minus 1 minus K2 into A21 minus A11, A21 minus A11 is 0, so into 0 and equal to 0. So we will have K1 A11 minus 1 equal to 0. This means K1 A11 equal to 1, and this implies that A11 equal to 1 by K1. So we have got this influence coefficient A11, that is when the load is unit load is applied at 1 and the displacement is being measured at 1. Now because A1 from equation 3, we have A21 equal to A11, and therefore it is also equal to 1 by K1. So we have got the second influence coefficient A21, that is when the load is applied at 1 and displacement is measured at 2. So and they are equal. So we have got these two influence coefficients. Now we have other coefficients that we need to find out, and therefore we will apply the similar process. So now so in the previous case we applied a unit load at 1, now we will apply a unit load at mass 2. So we can have so we will have this is spring K1, K2, and this is mass M1 and M2. Now in this case we are applying a unit load here, so let's we apply a unit load here and we measure the deflection at other places. So here deflection at this place will be A22, means we are applying a load at mass 2 and we are measuring deflection at 2, and this one will be A12. So we are applying load at 2, unit load at 2 and measuring the deflection at 1. Now we make the free body diagram of this equation, this load system. So we will have this first mass. So we have so we will have, and this is the second mass. So on the second mass we have this unit load plus this is spring force. So we will have this spring force K2 into A22 minus A12. So this is K2 into A22 minus A12, and similarly this force will also work on this mass because the spring is connected to the both, only the direction will be different. Now we have here, due to A12 movement, there will be a force K1 into A12. Now we apply the equilibrium equations. So here K1 A12 equal to K2 A22 minus A12. This is equation number 1. And then for this K2 A22 minus A12 equal to 1. So here A22 minus A12, so this is equation number 2, and from here we will get 1 by K2, this A22 minus A12. Now we put this value A22 minus A12 into this equation number 1. So this A22 minus A12, so we write K1 A12 equal to K2 into A22 minus A12 is 1 by K2, and so this will cancel out and it is equal to 1. So this implies A12 equal to 1 by K1. So we have got this influence coefficient A12 when a unit load is applied at 2 and we are measuring deflection at 1. Now we put the value of A12 in equation number 2. So from equation 2, if we put this value A12 here, so K2 A22 minus 1 by K1 equal to 1. So now we will have A22 equal to 1 by K2 plus 1 by K1, and so it is K1 plus K2 upon K1 K2. So this is another influence coefficient. So from the, we know that from the reciprocal theorem A21 equal to A12, and so that is we see A12 is 1 by K1 and A21 is 1 by K1. So even if we know from here A21, we don't need to calculate A12. We already can use this as the value of A12, and here A11 equal to 1 by K1 and A22 equal to K1 plus K2 by K1 K2. So now we know all the elements of this matrix, so we can write this matrix. So A equal to A11, that is 1 by K1, and A12, that is 1 by K1, and A21 is also 1 by K1, and A22 is K1 plus K2 by K1 K2. So this is the flexibility matrix that we can obtain. So I stop here and I thank you for attending this lecture. See you in the next lecture.